On the laundry list of topics that I intend to cover, machine learning is pretty high on that list. I recently gave a presentation about machine learning and neural nets in a graduate course and thought y'all would like to see it. So leave comments, let me know what you think about the presentation and what things you'd like to hear more about. If you liked it and you want to hear more, subscribe, hit the like button and the bell icon, and keep your eyes peeled for more content. Hey everyone, you're here to learn about machine learning and neural networks. So, let's get started. Over the next few class sessions, I'll be introducing you to one of the largest buzzwords in science over the past few decades, machine learning. This presentation will be broken up into 2 sessions. In this first session, I'll set the stage by presenting a motivating example. I'll follow the example with what machine learning is, and, equally important, what machine learning isn't. I'll transition into a brief background, tying the past and present state of machine learning to more commonly known methods and techniques. After the short history lesson, I'll dive into popular machine learning techniques and discuss problems they can solve. Finally, I will introduce neural networks and explain how they work and what problems they can solve. In the second session, I will walk through an example that implements a neural net and discuss the software options in case you want to learn more about machine learning and neural nets. It's no surprise, but teachers generally want the best for their students. They want their students to succeed and will aim to do whatever they can do to facilitate that. Of course, this relationship goes both ways. It's not solely dependent on teachers, nor is it solely dependent on the students. In general, it takes 2 to tango. Since students vary widely within a single classroom, it can be hard to balance the level of methods and materials that would best suit a group of students. Lowering the bar a bit for students who benefit from a lower pace or easier material may stall out other students, while raising a bar to push expectations may leave some students in the dust. Regardless of what students are bringing to the table, it's been noted throughout the years that across all other school inputs, teacher quality remains the leading lever in positive change for student success. So from a teacher's point of view, and speaking from some experience, it's not wise to bank on a classroom full of students who don't need your assistance at all. So in order to get the best bang for your buck, it's usually in your best interest as a teacher to know your students and the materials you're bringing to the table. And when it comes to materials, it's beneficial to have a surplus of materials than a shortage, so that you can pick and choose the best tools for the job at hand. Unlike the why, how to maximize your performance as a teacher has long been debated. Traditionally, teachers within a school would talk to one another to share strategies, ideas, and materials. If you've ever spoken with a teacher or taught yourself, you know it's painfully obvious when things work and when things fall flat on their face. So sharing these experiences with others allow them to stack their own tool belts with more tools for future use. What used to be an in-house affair has now exploded to a virtual conglomeration of available resources for teachers to swim through, utilizing anything they please with just clicks of a mouse. But with more materials came more questions. With a plethora of resources to choose from, how does one effectively sift and sort through them for their own use? Unlike the resources, a teacher's time is extremely limited, so it's not possible to spend hours on Pinterest. Then, even if you could effectively sift through them somehow, how do you know which resources are good? Surely, not all resources are created equal. So, which resources will really push your students' mental limits, and which ones will have them passing notes about how bored they are? Luckily, characterizing mathematical resources for students isn't a new problem. The framework to characterize content based on cognitive demand had already been developed using a framework called Bloom's Taxonomy. Using the 6 hierarchical cognitive levels required in human problem solving, namely remembering, understanding, applying, analyzing, evaluating, and creating, ranking materials on their cognitive demand breaks down to tedious sorting and cross-checking among others to make sure that the manual sorting is consistent. If you're going to sort resources by cognitive demand, it should be consistent which bin a resource falls in, or what are we doing here? The second question remained though, which resources relate to more student success? the more cognitively demanding ones, or the less cognitively demanding ones. Or maybe it doesn't matter how cognitively demanding they are. Who knows? In a pilot study, Pinterest pins by local math teachers were manually coded using Bloom's taxonomy, which were then fed into a model, along with student achievement data. The results spurred a larger nationwide study of K-12 math teachers and the materials they exchanged on Pinterest. The problem with scaling up was that the pilot study initially tested the hand coding with only 26 teachers, who had somewhere around 2,000 pins. Although we didn't know it at the time, scaling up to a sample of the entire country's worth of K-12 math teachers would mean coding over 2.5 million pins via Bloom's taxonomy. To say the least, we were short on volunteers. Although human coding was very precise, automating the coding process was the best feasible option if we wanted any chance to scale up. So, we decided to turn to machine learning. So, what is machine learning? As Tom Mitchell states in his 1997 book, Machine Learning, published by McGraw-Hill, machine learning is the study of computer algorithms that improve automatically through experience. Two key components make up the meat and potatoes in this definition: computer algorithms and automatic improvement through experience. We'll quickly get bogged down in terminology, like tires trying to spin while entrenched in a muddy pothole. So to keep things as simple as possible, machine learning is turning things like data into numbers, then finding patterns in those numbers. That's it. I say things because sometimes data isn't directly numerical, like pictures or voice. In those cases, turning those things into numbers is the first crucial step before looking for patterns. Turning things like pictures and voice recordings into numbers isn't all that complicated anymore. So the big question is the finding patterns part. This is where computers come into play. And how do computers find patterns in numbers? Math and statistics. Lots of math and lots of statistics. Although you may be hard-pressed to find anyone willing to admit this, machine learning has some serious limitations. Speaking of complex jargon, I'd like to put something out in the ether. The picture in this slide should look fairly familiar. No, not cricket chirps, but a plot of data points with a straight line drawn through them, some falling below and above the line. This is the example Google uses in their own machine learning crash course. It's an example of a simple regression, one dependent variable and one predictor. Since the recommended prereqs for this course are CEP 932 and CEP 933, I think it's highly likely that everyone here has performed a simple linear regression at some point before this presentation. If that's the case, then congratulations, you know a little machine learning and perform some yourself. No, it's not quite as mathematically sexy and savvy as you may have been expecting, but nonetheless, linear regression is one of the most common and simple forms of machine learning. Taking data, turning it into numbers, and finding patterns in those numbers. But machine learning is much more than just regression. It's a large umbrella that encompasses many different techniques that share the common mindset. It's a broad brush that covers a slew of methods that I will delve into next. But before I go into more detail, we need to take a quick history lesson. If you look up the inventor of machine learning, you'll stumble upon a man by the name of Arthur Samuel. He was an American IBMer who pioneered the field of computer gaming and artificial intelligence. He was the first to use the term machine learning. Although that's where the term comes from, regression and correlation trace back to the 1800s to Sir Francis Galton and Auguste Bravais. Bravais, who developed it first in 1846, and Galton, who reportedly rediscovered it independently later in 1888. In the early days, some researchers were interested in having machines learn from data. They attempted to use symbolic methods that were later found to be reinventions of the generalized linear methods of statistics. By the 80s, work on symbolic methods continued, but the more statistical line of research was now outside of the field of artificial intelligence. Neural networks research had been abandoned by AI and computer science altogether. Their main success came in the mid-1980s with the reinvention of backpropagation, the training bit of the process. Machine learning took off in the 90s when the field changed its goals from achieving artificial intelligence to tackling solvable, more practical problems. It shifted focus toward methods and models borrowed from statistics and probability. Machine learning and statistics are closely related fields in terms of methods, but differ in their goals. The major differences between machine learning and statistics is their purpose. Machine learning models are designed to make the most accurate predictions possible. Statistical methods are designed for inference about the relationships between the variables. According to Michael Jordan, the ideas of machine learning have had a long history in statistics and suggested the term data science as a placeholder to call the overall field. So, how exactly does this differ from computer programming and statistics? When people write code, they normally start with inputs, like data. Then they give the computer a specific set of instructions. Then the computer follows the instructions to a T to produce an output. I love to cook, and eat for that matter, so I always tend to use examples with cooking food. Traditional programming is like starting with a set of ingredients, then following a recipe to make a desired meal. This is where machine learning is very different. Machine learning starts with inputs and a set of ideal outputs, and tries to figure out the instructions it would need to follow that link the two. Once it settles on a set of instructions, it saves those instructions, so if it gets new inputs, it can create new outputs using the instructions. In cooking terms, this is like starting out with ingredients and the final meal, then analyzing both, attempting to write the recipe that must have been used, then using that recipe on new ingredients to make a meal. In this analogy, you can imagine that in order to recreate the recipe, it might help to see a lot of example dinners to get the recipe just right. Like I mentioned before, writing the recipe, or finding the patterns within the data, is the second step, where turning the initial data into numbers is the first step. This step almost completely depends on the specific problem at hand. How you translate onions, carrots, celery, raw chicken, and a delicious roasted chicken dinner into numbers may be drastically different than if you're trying to decipher pins on Pinterest. I mentioned that simple linear regression is a form of machine learning, and I wasn't lying. I want to walk through what is going on in a simple regression, but not because anyone here needs a re-lecture on y equals mx plus b, but because regression plays by the rules of machine learning. So I will translate step by step using machine learning lingo. Imagine you had data on the distance cars had traveled and the cost for each car, and you wanted to train a machine learning system to take in both the numbers of miles driven and the price of the cars. In this case, the relationship seems pretty linear, so we might be tempted to use a linear model of the form f of x equals a1 times x plus a0. This is your famous y equals mx plus b, where a1 is the slope and a0 is the intercept. In machine learning, we call a1 and a0 weights. And just like slope and intercept, they completely determine how the line looks and what outputs it produces for given inputs. Determining the right weights is the core of what is called learning. So when I say learning, I want you to think finding the right slopes and intercepts, or finding the right weights. Let's say that the correct choice for our weights, remember, those are the slope and intercept, are 5 and 0.5. This is the graph on the left. But if you change the value of a0, the intercept, to something like -2, you would get the middle graph. And if we thought the relationship between miles and price was actually much, much larger, say 8, our graph would look like the graph on the right. So how do we leverage the fact that we have the correct labels for the cars in the data to learn what the best weights are? This is where we use something called a cost function. Don't let the term confuse you, because this is something you know and have used before. In regression, A common cost function is least squares. As a forewarning, I'm about to go into some decently technical detail, so this is what goes on behind the scenes of SPSS and other programs, so you'll never probably have to do this yourself, but it's important to mention them because these are the building blocks where machine learning takes off, so I'm going to do my best to balance detail with the big picture. The goal of the cost function is to give us a number that tells us how good of a job our choice of weights did, a number we can compare with other choices of weights. The least squares cost function looks at the difference between what the actual outputs are and the outputs our weights give. Yeah, it squares them so positive and negative deviations don't cancel out in the summation, but big picture, it gives you a number that tells you how far the actual outputs are from the outputs using your weights. We call those residuals. The goal is to make this as small as possible, to minimize the sum of squared residuals. To do this, there are two options. We can either solve for the best weights mathematically, or we can estimate the best weights numerically. If we pick the math route, we would use standard calculus, derivatives. In math speak, we call this a gradient. We set the gradients to 0 and solve for the weights. If you're wondering why you would set the gradient to 0, this is what I mean by standard calculus. It's how we traditionally find maximums and minimums of a function. Feel free to ask this as a question as a follow-up, but I'm going to continue since we have a lot to talk about. This technique is nice because it can result in a formula for the best weights, so we can quickly compute the best weights for any set of data. Unfortunately, this isn't possible with all models. That's where numerical methods come into play. Numerical methods is just a fancy term for taking small, incremental steps towards the right answer, or the best weights. Once you have an initial guess at the weights, you can adjust the old weights by computing the gradient of the cost function and adding or subtracting it to get new weights. You keep doing this until the weights stop changing very much every step, known as converging. This crucial process is called gradient descent. Also note that I stuck an alpha in there. Changing this to anything other than 1 changes how much you adjust your weights every step. It's called a hyperparameter. Other machine learning techniques have their own hyperparameters that can be adjusted to achieve better performance. In some techniques, this adjustment is critical and can drastically impact how good a method works. One cool thing about this type of method is that it doesn't matter how many weights you use. Say we thought that trunk space was important to know. All we have to do is add in another weight, say A2, and we can use the same cost function, least squares, to give us the best weights. Welcome, multiple regression. This may seem obvious, but linear regression doesn't always work. It turns out that it only works best when there actually is a linear relationship between the inputs and the outputs. When the relationship isn't linear, we may want to use a different tool for the job, but we're going to play by the same rules of weights and cost function. A good example of non-linear problem is classification. Let's say instead of predicting the price of a car, we only care about if the car is expensive or not. We'll use the same features, miles driven and trunk size, but our goal is different. This is what we use logistic regression for, classifying data into groups. The setup is similar to regression. We need a model, weights, and a cost function. The inputs are the same, but the weights will be different, so that the output isn't the price of the car, it's the probability that the car is expensive or not. So we call the model G instead of F. You would have to determine what is cheap and what is expensive, but after that, you're set. One thing to notice is that our model is in the form of a fraction, and E even stuck in there somewhere. We do this so that the output is a probability. I'm sorry about it, but it had to be done. The cost function is different this time. Given our cars, we want to be able to tell for sure if the cars are expensive or not. That means maximizing the probability. I know it looks gross, but the big takeaway is that it's different than that of linear regression. It's not least squares anymore. So the function we want to use to get our weights is different, but we still use calculus to find the best weights. We turn gradient descent loose, and life is good. These are some of the big building blocks for machine learning. The model you want to use, the cost function you use to decide what model is good or bad, then the calculus to find the best weights for your model. And these are usually where different techniques differ. So I want to talk about some different techniques, the problems they solve, and a little bit about the building blocks they use. I promise I won't delve too deep in the details. Although I have been, and will continue to focus on one category, there are two main categories of methods. The first category is what I have previously discussed. They use inputs and outputs to learn what the best weights should be. So we formally say this group uses supervised learning, as they are supervised by the outputs. The data is usually split into two groups. One group is used to learn what the best weights are, while the other group is used afterwards to test how well the weights work. You may be wondering, Jordan, is it even possible to do this without using the outputs? How on earth would you go about this any other way? How in the world would you guess which cars are expensive if you don't define what expensive means beforehand? And you're right. That seems like a pretty lofty goal. With that said, if you've ever ran a principal component analysis or an exploratory factor analysis, then you're not so stranger to unsupervised learning as you might think. Unsupervised learning methods take a set of data that contains only inputs, and they find structures in the data, like grouping or clustering data points. The algorithm learns what the weights should be from test data that hasn't been labeled with expensive cars or cheap cars. Instead, it defines commonalities in the data to create its own categories, then categorizes new data into those bins based on the presence or absence of the commonalities in new data. It would be like finding that there was a group of cars that shared a lot of common features and happened to be blue. So thereafter, it would place new blue cars in this group. This is an example of cluster analysis, where data is split into groups called clusters, so within the clusters, data is similar according to one or more pre-designated criteria, while data drawn from different clusters are significantly different. There was a method back in the early 2000s that was the cool kid on the block for classifying. The idea was to use a line that could cut through your data points like a hot knife through butter. If you plotted your data based on two inputs, and your graph looked like this, you could imagine drawing a straight line like I have shown. Then, use that line to classify your data. Anything below the line might be expensive cars, and everything above the line might be cheap cars. Then you could take any new car and use that to identify it as cheap or expensive. Instead of using y equals mx plus b like regression, you can write a linear equation in what's called standard form. a1 times x1 plus a2 times x2 is equal to some constant c. This still gives an equation of a line, but it emphasizes the weights that will be given to each input used to create the line. Since inputs and outputs of already obtained data are used to find the best weights, this is a supervised learning technique. This method uses a clever cost function to gauge how good a line is at separating the data. Naturally, you would like each group of points to be far away from the line. The red point marked with the green line would be far easier to classify as opposed to the blue point mark that rides the line of expensive and cheap. Likewise, this red point mark is almost on the line itself. Expensive, cheap. If the line was a person, it'd shrug its shoulders and say, I don't know. The points that are closest to the line are problems. So we give those small distances a name, margins, and the points themselves are called support vectors. Hence the name of this method, support vector machine. Small margins are tough for classifying, while large margins make life easy for classifying. So the cost function that is used in this method does two things. It sets a minimum distance that all points should be away from the line to begin with. Then, it picks the weights for the line that maximizes the margins. The cost function in this slide ensures that the points are all at least one away from the line. Then, gradient descent is used to maximize the cost function. As you may imagine, this is probably something worth adjusting depending on the problem at hand and the units of the data. There are some downfalls to this method. Remember, linear regression only works best if a linear relationship actually exists? Well, this method works best if the data is actually separable. What does non-separable data look like? Maybe the relationship of cheap cars and expensive cars looks like this when you plot them using miles driven and trunk size. Drawing a line that separates this data wouldn't work so well. Since it came on the scene, there have been a few different remedies to this problem. One solution is to transform the inputs into a higher dimensional space, like 3 dimensionals, by adding a dimension that uses the 2 existing inputs. Since things would be 3D instead of 2D, you would use a plane like a knife, instead of just a line, to split the data into groups. This type of transformation is called a kernel. Hence, this solution is called the Kernel Method. Again, this begs the question if all data is either separable to begin with, or can be adjusted using this trick. And the answer is no. Although this method has evolved to separating data using non-linear lines and curves, it's probably better to think about this method as another tool in the toolbox that is good for data that is linearly separable to begin with. I'll go back to Pinterest to introduce this next method. If you know anything about Pinterest, there are basically 3 to 4 categories of pins on Pinterest. So if we want to look at how cognitively demanding a math worksheet is, we first have to separate the math worksheets from the rest of the pins. Again, this isn't very difficult by hand, but doing 2.5 million pins by hand just isn't an option. Our goal is to decide whether a pin is a math worksheet or not. And to do that, we'll use some features of the pin himself. For instance, whether or not there are numbers in the pin. That might be a good sign of a math worksheet. So we'll say if a pin has numbers in it, we'll label it as math. And if it doesn't, it gets labeled as non-math. Now, numbers wouldn't do it by themselves. Any pin that said top 10 or top 25 would be tossed in with the math pins, even if they were top 10 wedding venues, or top 25 ways to torture your significant other by using pallet wood to make end tables. So we add another question. Say if there are math symbols, like adding or subtracting. So a pin would be thrown in the math pile if it had numbers and symbols. Anything else would be called non-math. This type of flowchart is called a decision tree, and is defined by the hierarchical structure. They're great because they're relatively straightforward to understand how the model will predict a given input. So the question now is, how do you choose the features to use to make your tree? The choices you make can drastically impact how the tree works and how well it performs. The bad news is that building the best tree is what we call a NP-complete problem. This is math lingo for no computationally efficient way to get the best tree. The general idea is to pick features that split the data up well. There are a slew of different metrics to do this, so I won't go into them all. Just know that I picked numbers in pins because that does a good job of splitting the pins up, and symbols in pins does a good job of further splitting the pins. A method like this, that is so simple to employ, does come at a cost. In practice, trees tend to have very high variance, meaning the possible trees you'd end up with are highly variable and dependent on the data you use. This means that they may not perform well with test data or new data points. To combat this, you can eliminate branches of the tree that do not capture many data points, like pins. Let's say that there weren't very many pins that didn't have numbers, but had some symbols. To limit the number of possible trees, it may be useful to replace the right side with just non-math pins. This process is literally called pruning your decision tree. In this example, I chose binary questions, but that's not required either. Decision trees are easy to employ, and many believe that they offer the best out-of-the-box performance for new problems and domains. Before we turn the focus to one final model, I want to discuss something that comes up in all supervised models. It's called bias-variance trade-off. Leaving the definitions, integrals, and random variables out of it, this visual shows the relationship between variance and bias. When you're applying a method to a dataset in order to hit a target, like estimating a parameter, how well it hits the target is broken down into two measures: how dispersed the estimates are, and how far away they are from the bullseye. How far away the estimates are from the bullseye is called bias. The dispersion of the estimates is called variance. An ideal method minimizes both at the same time. Unfortunately, decreasing one of these almost always increases the other. Bias can be caused when we make wrong assumptions in the model, among other things, while variance can be caused when the method we choose is really sensitive to minor changes in the training data. Models with more features than data points are sometimes called overspecified, which leads to more variance in the estimates. In regression, using traditional ordinary least squares, the estimates are not biased by design. With this said, more complex regression techniques like lasso and ridge regression introduce a little bias in order to lower the variance, which can result in a lower combination altogether. Now I'd like to introduce the last method on the docket. And to do this, we need a quick lesson on how neurons in the brain work. This visual shows the different pieces of a neuron. It's broken up into three big parts: the dendrite and the cell body, the axon, and the axon terminals. The neuron takes in stimulus from dendrites from all sorts of places. If the neuron gets enough stimulus, it passes a signal through the axon and the axon terminals to the next neuron, which goes through a similar process. At the beginning, there are signals passing throughout neurons all willy-nilly, but as time goes on, certain pathways are utilized more often, while others aren't used at all. Through this, pathways cease to exist, while others grow stronger by neurons adjusting themselves to how much input they need to pass on a signal. For instance, your neurons didn't know what it was like for your hand to sit on a fiery stovetop, but after multiple experiences getting burnt, the amount of input needed to pass on the signal, "Hey, we're about to get burnt," is probably far less than it used to be. This ingeniously simple setup is the idea for our last method. This method is called neural networks. Direct inputs are used as neurons to signal to us what the outcome should be. Each input, just like other supervised learning methods, will be assigned a weight. Then the multiplication and addition of these, along with a function called an activation function, will produce an output. I think this is easier to think of using an example. Imagine you wanted to be able to tell what digit had been written on a piece of paper. A digit between 0 and 9. The goal is for the algorithm to tell us what number it is, or the probability that it is each number. What you could do is use every pixel in the screen as an input. Then, once you write a number, every pixel would have a value depending on the color. somewhere between black and white, or 0 and 1. So quite literally, we use every pixel as an input, x1 all the way to x784. Then, for every drawing of the number 9, like in this picture, the pixel will have a value between 0 and 1, depending on if it's black, white, or somewhere in between. That part is actually quite easy for computers to do nowadays. The next step is where things get a little more messy. After the direct inputs, the pixels, we add 2 more columns of neurons. Each column of neurons is called a layer. There's nothing special about 2, and there's nothing special about 16 in each column. These are more or less arbitrary. They don't stand for direct inputs, rather than a combination of direct inputs. The picture on the right is a snapshot of one neuron in the first layer. It is connected to all of the inputs, each connection having its own weight, just like in regression. Since this is the case for every neuron in the layers, it's understandable why things look so messy. It's quite literally a picture of every possible connection from layer to layer. The last column is the list of possible outputs, in this case, digits from 0 to 9. It's not directly obvious how inputs pass through all of the neurons in the layers, then magically pop out an answer. So here comes some more detail, but I'll keep it surface level enough as to not get bogged down. For every direct input, there is a connection to every other neuron in the next layer, where each connection has its own weight. Here is the snapshot from the last slide, blown up a little bit bigger so you can see. The neuron on the right has 784 inputs, the direct inputs from the picture of our drawn number 9. The value that is given to that neuron is literally inputs multiplied by their weights, then added up. This number is fairly arbitrary and completely depends upon the weights and the inputs. If we want a more hands-on control of every neuron, a constant is added to the end called bias. This is something we can do for every neuron, or just keep it at 0 if we'd like. What happens next is this number is passed through an activation function that turns it into a number between 0 and 1. A very common function used for this is called a sigmoid function. It looks kind of gross, so when I say sigmoid, I want you to think between 0 and 1. Once the neuron has taken the inputs, multiplied them by the weights, added them up, with or without bias, then use the sigmoid to get a number between 0 and 1, it then passes that number on to the next layer of neurons. This whole process is happening for every neuron. The neuron in the left image is the one we just talked about. The new neuron in the middle image is also connected to all of the inputs and has its own weights. The new neuron on the right is fully connected to the inputs with its own weights too. I can't stress this enough. Every neuron in one layer is fully connected to every previous neuron with weights. And every neuron sends its signal to every neuron in the following layer. In this particular model, there are 784 direct inputs, using the pixels in the image. Then, there is 16 neurons in the first layer, 16 neurons in the second layer, then 10 final neurons representing our possible digits. This means, in this rather small model, there are just under 13,000 different weights. And that's not including all of the possible bias terms you may want to add to the neurons. This may seem stupidly daunting, but hang with me for a second, because there's one trick of the trade we haven't covered yet. No one, and I mean no one, whips out pencils to work out linear combinations like this anymore. Even if you were using SPSS, SPSS wouldn't work out every neuron signal one at a time. This is where matrix algebra really shines. The calculation can be neatly written using matrix notation, where you stack the weights up in their own matrix A. You stack the inputs in a vector X, and multiply, adding in the bias if you would like. Once you're done, you'd still apply the sigmoid to change your output to something between 0 and 1. Since each row relates to a neuron in the next layer, this one-line equation would be required for every layer, after the direct inputs. But this looks way cleaner and way easier to digest, and computers are wicked good at repeated calculations, especially matrix multiplication. So even though we have just about 13,000 weights to deal with, matrix multiplication turns this into a far more manageable job. After the dust has settled from the matrix multiplication, every neuron at the end that corresponds to a possible digit now has a value between 0 and 1. Our hope is that the digit with the largest value between 0 and 1 is the digit that was written. But what if it's not? I talked about how the system takes in the inputs and spits out an output, but how does it learn? It uses what the other methods use: training data, a cost function, and gradient descent to find the best weights. We have to use some data that we have the correct answers for. Then we'll let the neural net make its guesses on what each one is. Then we'll use the cost function to grade how well it did. And finally, we'll use the cost function and gradient descent to adjust the weights. One cost function is just like the one used for regression. You take the outputs from the neural net, the numbers between 0 and 1 for every digit, then find the difference between the correct output, squaring the difference. In this example, the number is 3, so the correct output should be all zeros other than 1 for 3. Remember the dinner example? You want a lot of example dinners to get the recipe just right. So in this case, you want a lot of examples where you can compute the cost. If you had 10,000 written digits to guess, you could make guesses for them all, compute the cost of each one, and then just find the average cost. If this was large, the system is pretty garbage. If it's small, on the other hand, then the system makes pretty good guesses. Once it has that, a far more complex version of gradient descent is performed in order to find out which nudges to which weights should be made to make for a smaller average cost. I'm going to leave out the math for this one, but I have many resources that run through it if you'd like. Just ask. This process of adjusting the weights when you have the right answers is called backpropagation. The system works backwards to make the adjustments, but the adjustments are made from layer to layer. In other words, they propagate. In my motivating example, I shared a problem that the team Teachers and Social Media worked on, a problem that I had the pleasure of being a part of. They were able to use a neural network to help them classify the cognitive demand for pins via Bloom's taxonomy. But what really gave them success is that they had 2.5 million pins to help train their model. By the time their model had been adjusted, it knew every which way a math worksheet could look, and it had a very clear image of what each cognitive level looked like. Not only was the 2.5 million pins not an issue, it was a strength. They're still feeding the algorithm data to further adjust the weights, as the pins from Pinterest and from teachers keep flooding in. This topic is very, very broad. To be completely honest, even clever and complex methods I've shown you for neural nets are slightly outdated. There are newer, nuanced neural networks, such as convolutional neural networks and long-term short memory networks. My goal was to give you a big enough overview to feel more comfortable talking about machine learning, or at least not to avoid eye contact if it comes up in your next meeting. I also wanted to give you enough detail so that you can decide for yourself if neural nets, or any other machine learning method, may be something worth looking into for your own projects. If I've learned anything with the time I've spent making models and learning about machine learning, it's that everyone understands that this is a broad topic, and it usually needs to be custom tailored to the problems at hand. So in other words, you don't have to worry about running into a machine learning expert and being stuck with your foot in your mouth. At worst, you may encounter someone who was able to tailor a method to their problem and would be more than excited to share how they did so. We went over a lot, so I want to recap just a little. We talked about an example of where automating a simple process might be the only option. This is where I introduced machine learning. I talked about the meat and potatoes of what machine learning is, and made a loose analogy to cooking as an example. I talked a little bit about the history of machine learning, and how we're all actually already familiar with one of the most famous machine learning techniques, regression. I mentioned the idea of cost functions and gradient descent, and how they're used to find the best weights for a model. I talked a little bit about other methods, like logistic regression and decision trees. Then, I talked through how neurons in our brain inspired the idea of neural networks. I discussed the big ideas, some mid-level details, and tied in cost functions and gradient descent. Now that's all she wrote for session 1. In session 2, I will present a case study example, and we'll discuss the software options for machine learning methods that I talked about in session 1. If you like this video or would like to hear about other topics, subscribe, hit the like button, and leave a comment.